Hello everyone. So since it's 5:07 already, so now let's just start our workshop. So today we will be learning about linear and logistic regression. And before we start, let me just introduce myself first. My name is Jovan Hermawan and I am currently a second year IEM student. I am the subcommittee of the MLDA at EEE Club NTU under the academics and training section. So first, before we start our workshop, I also want to introduce our club first, which is MLDA at EEE. So MLDA at EEE is a student-centric lab which aims to provide a platform to empower our EEE or IEM students learning and deploying of machine learning and data analytics skills and knowledge in both academia and industry. We also impact knowledge and skills for machine learning through our 4 different pillars of events, ranging from our machine learning projects, industry projects, and also career events. And the last one will be workshops with competitions. So MLDA is currently having a flagship event, which is the Deep Learning Week, which is a 1 week long event that aims to promote machine learning and data analytics via industry sharing, recruitment booth. And on the first day, there will be industry night where we are doing a panel discussion with the experts from the field of artificial intelligence. And then in the end, there will be a virtual career booth from many companies, whereby participants can network with the company representatives and apply for jobs or maybe internships. So if you are keen on joining that, please register by scanning the QR code or going to the tiny URL that is given in this slide. So yeah, moving on. There's also another part of the Deep Learning Week series in which is the workshop, the Deep Learning Workshop series. And then we are conducting workshops for all levels of expertise from introduction to Python workshop up to the transfer learning. So this current workshop is the second workshop, which is the Linear and Logistic Regression workshop. So please stay tuned and see our social media, maybe follow it if you want to get more info on each workshop. All right then, so let's just start our today's workshop. Now, today's workshop will be divided into two sessions. The first one will be the theoretical presentation of linear and logistic regression. And then the second part will be the hands-on coding session. I will be covering the theoretical presentation of this workshop, and later on, my colleague Dewi will cover the hands-on coding session. So let's just dive right into the first topic of today's workshop, which is the linear regression. Well, we will be covering a little bit about supervised learning and also the regression problem. And then an example problem set will be provided to help us understand more about the linear regression. There will also, we will also dive deep about how to represent the hypothesis and how to find the best parameters for each of the hypotheses, in which we will be learning about cost function and how to use the gradient descent. So let's take a look at the graph, and let's just say that from the graph, the variable x is the size of the house and y is the price of the house. Well, I know the numbers might not make sense, but well, let's just assume that and let's play along with it for now. So given the data set, like the graph, let's say we have a house which is the size is around 70. So we want to know for how much can we sell the price for. How do we figure out how much we might be able to sell our house for? Well, one thing we can do is to fit a model. We can fit a straight line to the data of the graph. So it will be just like the red line that is already provided in the graph. So if we take a look at the point 70 of x-axis and draw a straight line to the red line, just like that, and then draw another straight line to the y-axis, so it will go like that. Based on that, maybe we can sell our house for around 20 or 19. This linear regression is a supervised learning. Why? Well, we get to decide whether something is supervised or unsupervised based on the training set. So if for every input feature there is also an output provided, then it is considered a supervised learning. So for example, as you can see from the graph beside the graph on the right, for every single dot, there is also an output as well. So if you look at the y-axis, there is an output for every single x that is there. So another example of supervised learning is when given pictures of cats and dogs, and then each picture is already labeled whether they are cat or dog. So in other words, we are already given the right answer for each of our input examples. Next, from the name, we can also already tell that linear regression is pretty much a regression problem. So regression problem is when we are predicting a real valued output. Now, this table on the right is an example problem data set which can be used as training example when using linear regression to predict the price of houses based on their size. So in linear regression, we will be working with a few symbols, and I will be introducing the symbols to you for this workshop. So the first symbol that we will be using is the M, which will denote number of training examples. Number of training examples is actually just the row of the table that is provided of the data set. So in this case, the number of training examples will be 4 because there is 1, 2, 3, 4 rows of the table. And let's say if there is 6 more of this table, then the number of training example will be 10. But in this case, since we're only working with this table, then the number of training example is just 4. Okay, moving on. The next symbols that I will introduce to you all are the X and Y. So X will denote the input variable features, and the Y will denote the output variable feature, which in this case, the X is the size of the house, and the Y is the price of the house. But why though? Why is the size of the house the X? Why is it not the Y? Because we are using the size of the house to predict the price of the house. So the one that is based on the one that we use to predict the one that we want is the X, and the one that we want to predict is the Y, which is why the size of the house from the problem statement here, based on size. This means the size will be X, and the price which we want to predict will be the Y. There is also an example of a training example, which will be denoted by parentheses X and Y. So one training example, for this case, we will need a pair of training example, which will be the X and Y. Which because of that, we can count the number of training examples based on the rows. So we cannot just say this as a single training example. We will need both the input and output to be set as a single training example if you're working in this case. But later on, in more complex machine learning problems, we will probably working with more variables in which there may be a house, the number of rooms in the house in this table, and there may be another variables which denotes more input variables. In that case, then we will need maybe x1, comma x2, comma x3, and so on until there is also the y. And this is what we call the training example, which is why the training example is just the row. So even if there is more of the table, more columns of the table going on, we can simply figure out the number of training examples from just looking at the row. Okay, moving on to the next. So I will introduce you to a notation which can denote the ith training example. So it is denoted by superscript. So let's say if we have x superscript 2, then it will denote the second input variable feature, which will be, in this case, will be the 1416, because this is number 1, this is number 2. So it will be this one. And let's say if we are working with y superscript 3, then it will be the 315, because yeah, this is the y and this is number 1, number 2, number 3. So that's pretty much almost all the variables that we will be using. So let's just move on to the next slide. But well, before diving deeper right into how to do the linear regression, we first might want to learn about the main pipeline of how supervised learning algorithm works. So to do machine learning, the most important part is the data set or the training set. Well, data set is crucial because we are telling the machine to learn by itself. So how do they learn without us programming every single steps? Well, we will need to feed them the data. So with the training data set that we have, we can then feed them to our learning algorithm. So in this case, the learning algorithm is the linear regression. Well, the job of a learning algorithm is to then output a function, which by convention is usually denoted by lowercase h, which stands for the hypothesis. The hypothesis will then take input features and try to produce the estimated output. So in other words, h is a function that maps from x's to y's. So in our example, the hypothesis will take the size of the house and will output the estimated price of the house, which it can be sold for. So just like the previous example, if we have a house which size is 70, that will be the input, and the estimated output will be the 20 or 19, which we get from reading the graph. Now, I also want to emphasize that the data that is used as the training set here, so the data of this training set is different than the data that is used for the input here. So the data that is used as a training set is the data set just like the previous table. Like as I said, all the x's and y's. This is the data that is used as a training set, because this is the data that we use to train our machine learning system to output our model function. Meanwhile, the input data here is the data that we want to predict the outcome of the data. So this is the data that you want to figure out the output. So just like the previous example, if you have a house which size is 70 and you still don't know the output of the price which it can be sold for, that is why you input the data to the model function or the hypothesis, and then you get the output which denotes how much it can be sold for. Now, how do we represent the hypothesis? In linear regression, the hypothesis or the function model will basically be similar to an equation of a straight line. So as you can see, an equation of a straight line will usually be like y equals to a, which is a constant, plus bx, which b is also a constant and x is a variable. So this one is actually similar. As you can see, the theta, there's the hypothesis function, which is denoted by lowercase h, is equal to theta 0 plus theta 1x. So we will need a few parameters, which in this case is theta 0 and theta 1. And we only need two parameters because which are theta 0 and theta 1. Because in this case, we are only working with a single variable linear regression. So in the machine learning world, this theta 0, since it is just a constant that stands by itself, it is usually called the bias. Meanwhile, on the other side, theta 1, because it is the coefficient of x, it indicates the significance of x to the output, which is why it is called the weight. So now let's take a look at a few examples. For the first example, our bias or theta 0 will be equal to 1.5 and the weight is 0. So if we want to draw it on a graph, it will basically just look like a straight line which intersect with y-axis at point 1.5 and have a gradient of 0. Another example, the line will intersect with y-axis at point 0 and have a gradient of 0.1 because the theta 0 is 0. Then it will mean the intersection with our y-axis at point 0. And the theta 1 is 1. That means the gradient of the line will be 1. So last example, it will be just as simple as the previous ones, which the intersection of the y-axis will be at the point 2 because the theta 0 is 2, and the gradient will be 1 because the weight or theta 1 is 1. So that is basically how we can see how we can get a catch of the hypothesis. Now, after knowing how to represent the hypothesis, we are now faced with another big question, which is how do we find the best parameters so that our hypothesis can produce a better output? So to answer that question, I will first need to introduce you all about error and also the cost function. Now, if you look at the graph, there are scattered dots all around the graph, just like this one. So the scattered dots indicate the real value, indicate the real value of the data. And then there is also the dotted line, which is this one. The dotted line is actually our function model or our hypothesis that we, just like the one that we drew on the previous slide. Now, what is the error? So the error is basically just the difference between the real value, which is the dot, and the predicted value or our function model, which is the dotted line. So what is the error of this? Hold on. What is the error of this dot? Then it will just be the distance of the dot to the point which is the closest to the graph, which is just a straight line, a vertical straight line to the dotted line, which will be this error. So how about this line? Then the error will just be this one, and it applies to every single dot. Next is the cost function. So the cost function is basically just half the mean squared error. So cost function is denoted by J, which is this equation. So the cost function is basically just half the mean squared error, as you can see from this formula. It is sigma, which is the sum for all the errors. This equation is basically just the error from all of each example from 1 to m, which is all of the training examples. And it is divided by the number of examples, m, to find the average or the mean. Now we need to square the error, which is, as you can see from this one, it is squared, because we want to find, we want to account only the positive of the errors. because as you can see, if you look back again at this graph, the error can be either positive or negative, because we're only subtracting the real value from the hypothesis, from the predicted value, if you look at this case. So if you subtract this one with this one, then it will result to positive, but if you subtract this one to this one, then it will result to a negative error. That is why, since we want to account only the positive ones, I mean, we want to make the negative to positive also, then we'll just use the square. So there's also a half. Now, why do we need to divide it by 2? Well, the half is basically just to cancel out the coefficient 2, which we will get after the derivative, which is why it is called the half the mean squared error. So later on, we might want to derive this cost function with respect to each parameter. And I will tell you more later on. Now, since we want our model to be as close as possible to the real value, then we want to minimize the error, which directly correlates with minimizing the cost function j. Now let's move on to the next slide. So to minimize the cost function, we will need to use an optimization algorithm, which is called the gradient descent. Just as the name says, this algorithm will be using the concept of gradient to get the minimum value of the function. So as you have learned in basic math, the gradient is actually just the derivative of the function. So let's say at first, our parameter θ1 will be at this point, which resulting to a high cost function, which is at this point. So this will be our starting point. What we will do is to just keep updating our parameter until we get the parameter when the function is at its lowest point. So our goal is to end at this point. Now, how do we do that? So we just have to update it. But how do we update it? Well, all we have to do is just to subtract the parameter θ1 with the derivative of the cost function j, with respect to the θ1, of course. So that then the point will move right, closer to the minimum point. So the point will, as the graph already draw, it will move closer and closer to the minimum point. But why? Well, that is because the gradient at this point is negative. So let me redraw this. So if I draw a straight line at this point, it will look like this. And as you can tell already, the gradient of this line is negative. So that is why if we minus our parameter θ1 with the gradient of θ1, of the gradient of the cost function with respect to θ1, which will look like this, then it will be just moving the θ1 to the right, because this gradient is negative, so it will be positive. It will be θ1 plus something, plus some constant. So it will hence move forward. And we'll keep doing that over and over again until we reach the lowest point of the graph, which will be our goal, which at that point will be where the cost function is at minimum point. It will stop at this point. It will totally stop at this point. Why? Well, that is because the gradient at this point, so let's say the derivative of the cost function with respect to the parameter θ1 at this point will be 0. That is why if we keep even if we keep updating the θ1 with the gradient, with the derivative with respect to the θ1, then it will be just basically θ1 minus 0. Hence, it won't move anywhere. Now, let's say if the starting point is instead at this side of the graph. Then, if we draw a straight line, we can tell that the gradient is positive. Hence, subtracting the gradient from the parameter theta will move the point backwards to the left. It will look like this until it will eventually reach the minimum point. Now, why do we need to use this gradient descent optimization algorithm when we can already find this minimum point just by using a closed form math equation, which is we just find the equation where it is the derivation of the cost function with respect to the parameter equals to 0. Using this equation, we can find the minimum point directly, right? Well, in the more complex machine learning problems, doing that will be very computationally expensive because the function might be very complex, and also we'll be working it with many parameters, which is why it can be very computationally expensive, or it can also even be impossible to derive directly the most optimum solution using this equation. That is why in machine learning world, we usually are using the gradient descent optimization algorithm. Now moving on to the next slide. So the graph in the previous slide is just a graph of the cost function to a single parameter theta1. So if you look again at the previous slide, this graph is just a graph of the cost function j with respect to theta1. But here we can visualize the graph j, which is our cost function with respect to all the parameters, which are the theta1 and theta0. This graph, which is called the contour plot or contour graph, is to visualize the correlation between the cost function and the two parameters and all the parameters. So to visualize gradient descent on this graph, we might want to imagine that we are standing at the top of the hill. So let's say our starting point is at this point, and we want to reach the lowest point of the hill in as few steps as possible. So we want to reach at the lowest point of the hill, which might be this point. We're using as few steps as possible. So what do we have to do? Well, all we have to do is just to follow the path that is the steepest. So let's say the path that is the steepest is using this path. And then we just take a little step, and we keep doing over and over again, following the path that is the steepest until we get to the point of the minimum, where there is no more path going down. Using that, by doing that, we can get to the lowest point with as few steps as possible. Now, I want to tell you that one important thing that we need to do in gradient descent algorithm is to update all the parameters simultaneously. So we need to update theta0 and theta1 in this case simultaneously. And since in our case we are only dealing with a single variable linear regression, then we only have to update two parameters, which are theta0 and theta1. But in most cases, we will need to deal with multiple variable problem. Hence, we will also need to update all the parameters simultaneously. Now, why simultaneously? Well, that is because we want to find the minimum value of the cost function with respect to all the parameters, not only just a single parameter theta1 or theta0, but we want the lowest point of the cost function with respect to all the parameters. So we count all of the parameters. This equation on the right, this one, is just the derivative of the cost function with respect to theta 0 and the derivative of the cost function with respect to theta 1. So if you look closely, this is just the mean of all the errors, because this is the error and this is to sum all the errors, and by dividing it by m is just to find the average of all the errors. So it is actually pretty simple to be understood. Now there is also actually a symbol that I haven't talked about, which is the alpha. This alpha is a variable that we want to use to control our optimization's step size. By step size, I mean hold on, let me move back my slides. By step size, what I mean is the distance from this point to this point. That is called the step size. All right, going back. All right, so the cost function, if you can recall, I'll give it back to take a look. The cost function is 1/2 the mean squared error. So as I said previously, half is to cancel out the coefficient that we will get from derivating this function with respect to the parameter. That is why now the derivative of the cost function with respect to theta 0 and theta 1, there is no more 2. There is no more 2 because it is already cancelled out. All right, so as I said, this parameter theta, this constant theta, is actually a really important thing that we have to make sure that we pick the right alpha in each of our machine learning system. Why? Well, let's take a look at the next slide. Now, the alpha is actually really important because if we take a look at the left graph, the step size is really big. So in this case, our starting point is at W0. So when we start at W0 and we use the gradient descent algorithm, it might move further away from the minimum point from this point. So our target is to move to this point, but our step size is actually bigger than that. So we will move across the minimum point to W1. And then since the gradient at W1 is even larger than the gradient of W0, then it will move even further away from the minimum point, which it will move to W2, and then it will continue doing that, so and so on, until it will just diverge. So we do not want that to happen, which is why we use the variable alpha to control that. So maybe let's say using the same graph, if with alpha equals to 1, which is the basic, which is when we ignore the alpha, then it will move to this point, to this W1 point. But maybe we can use alpha equal to 0.5. Then it might go across this point. But we do not want to use a very small alpha. Why? Well, because having a small alpha means we use a small step size every time we update our parameters. And having a small step size means we have to do the updates and the iterations even more times. And that will be really costly in the time aspect. That is why in every single of our machine learning system algorithm, we might want to find the right alpha, which is not too small and also not too big. Now let's move on to the next slide. The previous counter plot, the previous counter plot that I showed you, which is this one, is called the convex function because it is shaped convexly just like a ball. But gradient descent will always work at convex function. It will always work at this kind of function, which is just shaped like a ball, and there is no other complex shape of the function. However, if we are being faced to a non-convex function, which might look like this one, then the gradient descent might sometimes not work well. In this counterplot, there are two types of minimum point. So the first one is this one, which is the global minimum. So the global minimum is the minimum function, is the minimum point which of the function of all the graph. So there is no single point that is lower than this point. But there is also another kind of minimum point, which is this one. This one is called the local minimum. It is called the local minimum because it is only the minimum point for a certain area around it. But if you look from further away, if you take account of all the graph of the function, then there is still a lower point that is even lower than the local minimum, which is our goal, that is called the global minimum. Now, let's say we are lucky and we start our gradient descent at this point using the parameters at this point. So if you don't know about counterplot and you don't know how to read it, so it will basically just in this point we will be using parameter theta 0 of around this, and we'll be using parameter theta 1 of around this. So if we are lucky and we get to start our gradient descent at this point, then by using the gradient descent, we can end up at the global minimum, just following the path of the steepest way. It will lead us to end up at this point. But let's take another example. So let's say if we are not really that lucky and we start at this point instead. So even with just a small difference between our starting point, it will result to a different result, which the first one will result to the global minimum, and the second one will result to local minimum. So if we want to handle a problem like this using the gradient descent, we can actually do the gradient descent several times, each of them using different starting parameters. So let's say we use the gradient descent several times using different starting points, just like this. Let's say these are all the starting points. So there might be some points which will lead to the local minimum, but there is also some points that will lead to the global minimum, such as these points. So then all we have to do is just take the one that leads to the global minimum. But of course, we don't have to do the gradient descent several times if you're dealing with the convex function, just like the previous graph, like this one, because we will always end up at the global minimum. Now, in most cases, we would be only facing with a single variable linear regression, because there is usually more than one deciding factor of how something is obtained from. So for example, using the same house example, just like the previous table, we can actually also account the number of bedrooms, the number of floors, and the age of the house to predict the price of the house. When previously we are just using a single variable x, now we will need more variables. And usually we just use subscript 1, 2, 3, and so on. So in this case, this will be our x subscript 1, x subscript 2, x subscript 3, x subscript 4. And this one is not x subscript 5, because this is the one that we want to predict, which, as I've already told you, the one that we want the result, the one that we want to estimate for, is called the y. Now, for that, for each of the single new input variable, we will also need theta, which is the weight for each of the input variable, which is why there's theta1, there's also theta2, theta3, theta4. And if there's more, it will just go like that and so on. So all of this theta1, theta2, theta3, and so on, is also still called the bias. No. It is also still called the weight because it indicates the significance of the input variable x that is paired with it. Now the only one that is called the bias is only the theta0 because, as I said, it only stands by itself. Yep. Now let's move on to the next slide, and I will introduce you to how to factorize our data. So in the programming world, it will be inefficient to code a program that looks like this. That looks like this, because it will take more time and it will be just more troublesome to maybe look at it. So what we want to do is to factorize them. We can factorize all the input feature x for a single example as a column factor. So all these x, x1, x2, x3, and so on can be factorized just like this one. And then on the other hand, all the parameters can also be factorized just like this one. Now, since we want to represent the hypothesis using this factorization, using this factor of each input features and also the parameter, then the formula will be this. The formula that we will be using will be the theta transpose times x. Because if you have learned about matrix multiplication, then this times this theta transpose, which will look like this. And if we multiply it by the column factor of x, which will look like this, then it will result to this previous hypothesis of ours. Now, there is actually a new variable that I haven't discussed, which is the x0. So in factorization, we will need to use x0 to make sure that we can multiply this factor to this factor, because we will need the same size of the factor, right? Now, the x0, if you can already guess, then it will be 1. Why 1? Well, because if you look at this formula, it will be theta transpose times x, right? Well, the theta transpose, which will look like this, and this will be theta0, will be multiplied by the first row of this factor, which the first row which will be x0. Now, since what we want to get is back to this formula, which will look like this, then the theta0 is just standing by itself. It doesn't have any coefficient. So in that case, its coefficient will be just 1. That is why the x0 is 1. Now, in picking the input features, we usually will take a look at the correlation between the input feature and the output. However, correlation doesn't always mean it is the right input feature that is used. Let's take a look at this example. Between the graph of US spending on science, space, and technology and the graph of the number of suicides, there seems to be a really high correlation between these two. But in reality, these two just doesn't affect each other at all, because they don't make sense at all if we are trying to see a connection between these two. So which is why correlation is not always the causation, which is also why we'll need to find the right input feature for each of our machine learning system, because we do not want to just use the feature that has the high correlation, but actually doesn't make any connection between it. Now, that is actually the end of the linear regression topic. Now we will move to the second one, which will be the logistic regression. We will be learning about activation function, and then later on we will also be learning about the cost function and gradient descent again. But this time it will be for logistic regression. Before learning about logistic regression, I want to show you guys a classification problem. So let's say if we have this training set and we want to fit a straight line that can represent the data as well, maybe we will get a hypothesis that looks like this. So if we want to make predictions whether the tumor is malignant or not malignant, one thing we can try doing is to threshold the classifier output at 0.5. So the 0.5 will be at this point, and hence it will be thresholded at this point, which means if the hypothesis outputs a value that is greater than or equal to 0.5, which will be at this side, then we can take y equals to 0, or just predict that the tumor is malignant. However, vice versa, if the output of the hypothesis is less than 0.5, which will be the left side of the point, then we can take y equals to 0, or conclude that the tumor is not malignant. So in this particular example, using linear regression for classification problem might seem reasonable. But now let's try changing the dataset a little bit by just adding a single training example. However, it is way out there on the right, just like this. This will change the hypothesis function. If we now run the linear regression, we will instead get a straight line that might maybe look like this. And if the threshold hypothesis is still at 0.5, then it will be at this point. We will end up with a threshold that's around here. So that everything to the right of this point will be predicted as positive, as malignant, and vice versa. So everything to the left at this point will be predicted as 0 or not malignant. However, as you can already see, this is actually not a great thing to do, because by just a single training example at this point, it will result to a false prediction of these points, because these points are actually malignant, but because our function model is now like this will be predicted as not malignant because it is at the left point, at the left side of the threshold point. So applying linear regression to a classification problem often is not a great idea. Well, now we will introduce you to the logistic regression. So in logistic regression, we want our hypothesis to always be between 0 and 1. But how do we do that? How do we just make the hypothesis always be between 0 and 1? Well, we will need a function, which is the activation function. And in this case, we will be using the sigmoid function. The sigmoid function, because it is often used in the logistic regression, it is usually also called the logistic function. So all we have to do is to just use the theta transpose x, which is this one, which is the previous hypothesis formula for the linear regression, as the input for this sigmoid function. So this theta transpose x will be the z, because this g function denotes the sigmoid function, and then the input will be at this point, which is why our hypothesis function for logistic regression will look like this, which this one is just the hypothesis for the linear regression, but we have to use the sigmoid function. Now, the sigmoid function will look like this. So if we are using the threshold at 0.5, which is at this point, just like before, then for every z value that is bigger than or equal to 0, as you can see, we are thresholding this graph at 0.5, and it happens to be at this y-axis, which is why then all the z values that is greater than 0 will then be considered as 1. Meanwhile, all the z values that is lower than 0 or negative will then be considered as 0. And just to make sure that you still remember, z is the previous hypothesis function of linear regression, which is the transpose of theta times x. Now, let's take a look at an example. Let's say we already have got our hypothesis using the logistic regression, which will look like this. So this will be our z, right? Because this is the input for the g function or the sigmoid function. So it turns out, let's say it turns out that the best theta 0, so the theta 0 that we get is -3, the theta 1 that we get is 1, and the theta 2 that we get after using the gradient descent for logistic regression is also 1. So if we draw this equation, if we draw the equation of z, which is this one, at this graph, then it will look like this. And from before, since we are using the sigmoid function, then for every z value, which is this equation, this is the z, for every z value that is greater than or equal to 0, then it will result to a prediction of y equals to 1, which is why at this graph, the 1 or the positive, or let's say if we're working with the same problem as before, which is predicting if it is malignant or not, then this will be predicted as malignant, as 1 or positive. Because if you input the x1 and x2 at this point to this equation, then it will result to a number that is greater than 0. Meanwhile, on the other hand, if you input, let's say, x1 of 0 and x2 of 0, then it will result to a negative value because -3 will be less than 0, right? And then it will result to a prediction of y equals to 0, which at this graph we denote it using circle, and the positive one we denote it using x. Now that is why a logistic regression is really widely used in classification problem like this. Now moving on, this is the cost function for logistic regression. So it is divided into two parts, but this is actually just the cost function for a single training example. So it is not the sum of all. So this is basically just the error. Now the error is divided into two parts, which is for y equals to 1 and y equals to 0. And you can see the graph will most likely look like this. So this is actually really simple to understand. We want the cost function to be as small as possible. And if we take a closer look, when we have both y, the real value, and the predicted value also equals to 1. So as you have already known, the predicted value is this one, is the h function of x. So if both this and this is equal to 1, then we will be using this equation, right? So if we put in minus log 1, it will be equal to 0, which is right because our predicted value is the same as our real value, which is both are 1. So if you look at this graph, which is for the y equals to 1, if y equals to 1 and we have the predicted value also 1, then it will result to a 0 cost function. However, if our predicted value is instead 0, then it will result to a minus log 0, which will be around infinity, because log 0 is minus infinity and it will be times by minus, so it will be around infinity. So which is actually also very intuitively also easy to understand, because the real value is 1 and the predicted value is 0, so it is really different, right? That is why the error will be very big. And this one for the y equals to 0 will just be the same as y equals to 1. So if the y equals to 0 and the predicted value also equals to 0, then it will be just minus log 1, which is a 0, because it is correct. The predicted value is the same as the real value. And instead, if the predicted value is 1, then it will result to a minus log 0 again, which is also infinity, as you can see from this graph. Now let's move on to the next slide. Now, since in logistic regression, the errors are always positive, then we don't need to square the error because all the errors are already positive. Hence, the cost function will just be the mean of all the errors, which it will look like this. Now, you might come to a confused state because, whoa, we at first just using this kind of function for our error, for our source function, but now we suddenly get this kind of equation. Well, this and this is actually just basically the same, because let's say if we input the y equals to 1, then we will be using this equation, right? If we use if we have y equals to 1, then we'll be using this equation. Now, if we put in y equals to 1 at this equation, then it will result to this equal to 1, which means it will be 1 minus 1, which will be 0, and it will cancel out this entire equation, and this y will be just equals to 1, and it will leave us to just this equation, which is exactly the same as this equation, but the minus is at the outside. Now let's also take a look at y equals to 0. So when y equals to 0, this equation will be cancelled out by the 0, because y will be equal to 0. And in this equation, 1 will be minused by 0, which will be 1. And then it will leave us to just this equation, which is also exactly the same as this equation, but the minus is outside. So since this is just the error for a single training example, our cost function, we want it to be for all the training examples. So all we have to do is to just sum for all the training examples from 1 to m, and we divide it by m to get the average. So since in the logistic regression, we don't need to square the cost function, so we also don't need to divide it by 2, because there is nothing that we want to cancel out. Now the optimization algorithm of the gradient descent is basically just the same with the previous linear regression. So we just update all the parameters, let's say theta 0 and theta 1, using the using by we just update it with the subtraction of the cost function with respect to the parameter with each parameter. And it is good to also remember that we need to update all the parameters simultaneously. So the gradient descent optimization for this logistic regression is basically just the same as the linear regression one. Now moving on. So in the machine learning world, when a data set is provided, we might want to divide the data set into 3 sections. So the sections will be training set, validation set, and also the test set. Now, why do we want to divide all the data sets to 3 parts? To answer that, I will first just tell you about the function of each kind of data sets. So training set is the one that we want to use to train our function model. So our function model or hypothesis will fit this training set because we use the gradient descent algorithm based on the training based on the training data sets of this training set. So it will just fit to the lowest point of the cost function with respect to the training set. It will just basically it will just account all the training set examples. Now there's also the validation set. So validation set is the one that we want to use to check when to stop training our function model, when we want to stop optimizing our function model. We can do this because validation set is an unbiased data set. Now, what do you mean by unbiased? Well, to get to know more about unbiased, let's get the meaning of bias first. Biased is when the model is built based on the data set because the model is built to fit the data set. Hence, since we do not fit the validation set, since we do not use the validation set to train the model, to train our function model, then the validation set can be called an unbiased data set. So let's say this training set is actually the biased data set because we use it to train our model. But this validation set, we don't use it to train our model, which is why it is called the unbiased data set. So why do we sometimes want to stop training our model when we haven't reached the lowest cost function of the model? Well, that is because the cost function here is only fitting to the data set that we use to train, or in other words, the training set. So if we keep training it just to fit the training set, then it might cause an overfitting. Overfitting is when the cost function is really low if it is tested against the training set, but the cost function will be really high when tested against data set other than the training set. So let's say we test our function model using the validation set, then the cost function, if it is tested against the validation data set, can be really high because the cost function is only fitting to this training data set. But when it is tested against other than this training data set, it can be really high. So this is why we want to keep testing our function model against our validation data set throughout our optimization, because we want to know when to stop training our data. So when you're doing the machine learning in real life, we might want to stop training at the point when the cost function of the model against the validation set is rising again. So let's say this is the number of iterations. This is the number of iterations of optimizations that we are doing. And then this will be the cost function, the y-axis. Let's say our cost function is at first at this point, and then it will go down. But if we keep updating it just to fit the training set, it might then rise up again because it will just fit the training set data, but it won't fit all the data other than the training set, which is why it is called the overfitting. And then the last section will be the test set. The test set is basically the set which we want to use to test our model's final accuracy. So after picking the best model according to the testing against the validation set, we can finally use this test set as a new unbiased data set other than the validation data set. Why do we need this test set when we already have our validation set which is already unbiased? Because we have already used the validation set to pick the best model or to know when to stop the training of the function model. So to get better accuracy of our function model, we might want to use a new unbiased data set other than the validation set, which happens to be the test set. So in the machine learning world, when we are already given a data set just like this, then usually the section will be like this, which is 60% we will use it as our training set, and then 20% we will use it as our validation set, and then the 20% left will be used as the test set. Now that is the end for the presentation of theoretical part for this workshop. For the next part, I will be passing it on to my colleague Dewi, which will be covering the hands-on workshop coding session. Dewi, are you there?
Yeah, sure. All right, so sorry. Okay, so with that, let's get started into our coding session. I'll send y'all the link for the materials. Please let me know if y'all can access it. Yeah, it's in the Zoom chat. Okay. Okay. Can y'all access the workshop? Like this workshop folder. In it, you should be able to see the data sets we'll be using later, diabetes and grad admission CSV. And you can click this, open the link to the notebook. Oh, no. I do not want that. Yeah, y'all will need to open it with Google Colab. So, yeah. Before you do that, right, make sure that when you open the workshop, you create a shortcut to your drive. So you see this thing here. Y'all need to like click this triangle, drop down, then you add a shortcut to this folder to your drive. Only then will it work. Yeah. So if anyone has any issues, please raise your hands. If not, I'll assume that everyone is able to like join this, like view this notebook. So with that, let's get started. Okay. By the way, in case y'all don't already know, a quick way for you to run your cells in Google Colab is to actually click Shift Enter. So before we do anything, right, we need to kind of mount the notebook into your drive so you can access the data. So when you run this first cell, what you'll get is this. Oh my God, okay. Just give me a while to connect. Okay, you'll see this thing. You click the link here and you'll be prompted to sign into your Gmail account. So you do that and you'll be given like the authentication code token. Yes, just copy, paste. Give it a while. All right, so moving on, you want to go into like change your directory, go into the actual workshop folder so you can access the data sets. All right, is everyone okay? Yes, everyone is able to run up to this point. if any point of time during the coding session, y'all are like lagging behind or you don't understand something, feel free to raise your hands and one of the MLDA helpers will actually like invite you to join a breakout room to settle any doubts. Okay, with that, let's get started. So first thing you do, right, you run all these basic libraries. So this is like NumPy, Pandas, Seaborn, and Matplotlib. Those are for plotting our graphs later. So you just run that. Yeah, pretty simple stuff. So what we want to do first is actually perform linear regression on the grad admission data. So we want to see the likelihood of someone getting admitted into grad school based on some criterion. So first things first, we want to import our data set. So how we do that is we actually use the read CSV function. So we say our admission data is, oh wait, I already put it there. Okay. Let's say we label our data as admission data and we want to read the CSV file, which is grad admission CSV. And head function shows us like the top 5 rows in our data frame. All right. So you should be getting this. Everyone's okay, right? Chat. Oh dear. Oh, can you intro again the first part for Colab? This is my first session. Hi, Satish. Is there anything you don't quite understand about Colab? You can unmute yourself, or you can just like chat here. Or alternatively, you can message one of the helpers. How do I open this file in Colab? Okay, if you are having trouble, I see that you're on an iPad. I don't know if you can actually run Google Colab on an iPad. I've never tried it before. But by right, if you're on like a computer or a desktop, you should be able to right click this. You'll have the option to open it with Google Colab right here. I'm not sure if you can do that with an iPad, to be honest. So yeah. I have a desktop beside me. Yeah, please use your desktop. I've never tried Google Colab on an iPad. So sorry. Okay. Anyways, I'll move on. If you have any queries, you can actually private message any of the helpers, which has like MLDA in its front name. Yeah. Okay. So on to our linear regression. What's the most likely thing universities or schools look at when they want to admit students? Your score, right? I mean, I'm assuming that's how you go into NTU. You did very well for your test. You have a GPA of sorts. So let's do a linear regression model by looking at one variable first. In this case, our variable would be the CGPA. So our model is A, our weight, and our bias, B, A times CGPA plus B. And that will be your chance of admission. So we extract the following like columns, like you see these columns, we extract it into their own data frame. So what we do here is we actually chance of admit, and here, this is the name of the column, CGPA. Yeah. So from there, right, when you want to do linear regression, there's actually a super handy like scikit-learn library for linear regression. You can learn more about it here on the official documentation. So actually, right, you can just import like the linear regression model, and from there you can do all your linear regression. Okay, so what we want to do is we import the model from sklearn, and then we have to split the data set. Remember earlier Jovan talked about splitting it into the train, the test, and the validation data set. In this case, we don't really need the validation data set, so we'll just stick to train and test. So this function, how this function works is, if you take a look at the docs, it accepts your array of data as well as some other options. Yeah, you can read more about it on the docs here. But as you can see, it's your function, your X data, your Y data, And this test size is like a ratio of the size of your test data over like the whole data thing. So X and Y is your predictor, this is your response. All right, so let's type that here. We already have our class, our chance and CGPA data frame. So we're gonna put in CGPA first, followed by chance. Just to check, everyone is okay up to this point, right? Is anyone having issues or? All right. No? Feel free to unmute and like just protest at any point, yeah, if you are not getting it. All right. So now we have our train and test data set in place. We can just do a heat map to check on the correlation between the two. So as you can see, this is the correlation between chance of admission as well as their CGPA. And it shows that it gives a correlation of 0.87, which is pretty high, right? It's close to 1. So this indicates that, like, yeah, your CGPA might be pretty important when it comes to predicting whether or not you get admitted into grad school. So along with the linear regression, as I mentioned earlier, what you need to do is import the linear regression model from the scikit-learn library. And what you do is you actually type in this line here. You import linear regression library, and you have to create a new linear regression object. And I'll call it linreg here. Afterwards, you fit your your X and Y data set into the object. So the code is actually your X train from previously after splitting it, followed by your Y train. Yeah. And then we print out the intercept, your bias, as well as your coefficient A. Oh, I'm sorry, intercept B and your A, your weight. All right. Everyone's okay up to this point, right? Okay, I'll just take it as everyone is A-okay. So at this point, we already have a model of sorts. We have our coefficient, we have our intercept. So we can actually try to plot the line of our linear regression model above a scatter plot of the actual data. So what we want to do here is actually compare. So you can see that the scatter plot, right, it shows the actual data, these individual circles right there. And your red line is the linear regression model you just created. So you can see how well it actually fits with the actual data. And you can see it's pretty good fit, right? Like it's around there, it's a straight line. You have some outliers here and there, but generally it's, it should be a pretty good fit. So you want to evaluate how well your model actually predicts your chance of admission with regards to CGPA. And as Jovan mentioned earlier, there were some matrices you can use. So the first one is the mean squared error, which we explained as well. And then we also look at explained variance. So your explained variance is 1 minus, SSE stands for sum of squared error, and 1 and SST stands for sum squared total. So you can see it's actually the same, like not the same. It might be deceiving, but as you can see here, your SSE is this triangle. Is it a bar or hat? I can't remember the term. But your SST is a bar. So the difference is your triangle is your predicted value, whereas the bar is your mean. Yeah. Is there any confusion with that? Yeah. Y'all understand the difference between the triangle Y and the hat Y, right? Bar Y, Y bar, yeah. So that's one of the matrices we use. And then we have your root mean square error, which is actually just the root of your mean square error. Pretty self-explanatory. So what we want to do now is we actually want to check how well our model, like we want to evaluate the performance of our model. So what we want to do here is we predict the chance of entering admission using your train dataset. And from there, you can see that the variance is quite high. The higher your variance, the better it is, because it means that your SSE is lower, right? And you want to minimize your mean square error. So this is pretty good. So for this one, we try to predict it with regards to the train data set. And this one, we try to predict it with regards to the test data set, sorry. Yeah. You can see that the red dots is the predicted values corresponding to the CGPA, whereas the green dots represent the actual values for the real data. And we want to evaluate the model again. And we see that, yeah, it does a pretty good job. Your mean square error is relatively low and your variance is high. So that's what we want. But obviously, CGPA isn't the only thing that grad schools consider when they want to let someone in, right? So we can actually try to create a multivariate linear regression model. So we take into consideration the other factors as well. So here I put a regression model where I just dump like every single other column. You can, if you have time, you can try and play to see how well the model fits if you remove some factors. Yeah. So this is what we want to do. We want to extract the response and the predictor variables. We already have our chance of admission for the Y data frame, and we want to take from the X. So I'm just going to type out like every column here. Oh, sorry. SOP, LOR, your CGPA again, as well as your research. So with that, we have our X and Y. Oh, yikes. Let's see what's the issue here. Hold on, we have technical difficulties. Oh, okay. When you put in multiple column names, you have to put it in an array. So that's what I forgot to do. You need to add in this extra square bracket. My bad. All right. Okay. So with that, we're going to repeat the same process of splitting the train and test data set. So here we put our X followed by our Y. Okay, as you can see, we have 7 variables for our, 7 columns for our X data set now, because we do consider multiple variables. We can do the same thing as earlier. So we plot out our correlation heat map. And you can see the correlation of different variables with one another. Actually, if you look at the chance of admission, you'll see that CGPA still remains as like the highest one. Like it has the strongest linear relation with CGPA. But the other variables do play a part as well. Yeah. And you can actually just repeat the same process you did for univariate linear regression, but this time you're just using the new data set with all these other predictors. So you have your bias and then your your respective weights. Yeah. So what we want to do is we want to predict the total values from, from your predictors. So we want to try predicting based on our X train, which is our training data set. And we also want to try predicting based on our test data set. So you can put right there, X train, X test. As you can see, the blue one is the predicted values corresponding to your train data set, and the green one is the test data set. it's still a pretty good fit, right? Like, oh, the the points are scattered in a nice line right there. And so is the other one. Now we want to check on the performance and evaluate the model. So we do the same thing. And we can see that, yeah, it's a good model. You have a high explained variance. Your mean square error is relatively low. Okay. Is everyone okay up to this point? I'll take it as a yes. So everyone has completed linear regression. So congrats. You have just created your, I don't know if this is your first, but you have created a linear regression model. Okay. So now we'll move on to logistic regression, which is kind of the same logic as linear regression, but you have that extra function in order to determine if it's like a yes or no, 1 or 0. So once again, we want to, for this exercise, we're going to see if someone's going to get diabetes based on some factors. So we're going to do the same thing again here. As we import our data set. Let's call it diabetes data. And our file name is diabetes CSV. And I want to see just like a glance, a quick look at what I'm about to get into. So we see that the factors we're going to consider is actually the number of pregnancies this person has had, their glucose level, blood pressure, skin thickness, insulin level, BMI, diabetes predictor function. If y'all don't know, it's basically just like the likelihood of them getting diabetes. Y'all can look it up. Their age, and this is actually the final outcome. So whether or not they do get diabetes. Oh, yikes. Usually I'm just gonna ignore that. Usually you can do feature selection when you want to perform logistic regression, because surely like you can't consider every single variable you see. So there are some like methods for that, such as recursive feature elimination or say principal component analysis. But for the sake of this exercise, we'll just use a bit of common sense. And that common sense is we will be ignoring skin thickness as a variable when considering whether or not someone will get diabetes, because I don't really see the correlation between skin thickness and diabetes. Maybe it's like the thicker their skin is, the harder it is for the mosquito to suck their blood. So we're just going to ignore that. And what we're going to do is extract all of the other variables right here. So from that, we have our X and Y data frame once again. Okay. I think y'all know the protocol by now. We split into train and test size, and then y'all can play around, see how different test sizes actually affect the performance of the model. Yeah. So we have X, Y. For this sake, I'm gonna put a test size of 0.4. Yeah. Scikit-learn also has a linear regression model in addition to the logistic regression model. Actually, scikit-learn has a lot of like libraries and models for your classification, machine learning, etc. You all can check it out. So we're gonna create the logistic regression object. And then like for linear regression, we're going to fit it to our data. So we're gonna fit the train data, Y train. And afterwards, we make a prediction based on our test data. Okay. Y'all don't see anything because we haven't drawn anything yet. But you can actually evaluate the model based on this thing called a confusion matrix. Okay, don't get confused. I'll explain things soon. So the confusion matrix shows how many of your outcomes are actually correct, incorrect, and which one, it shows your outcomes the predicted outcomes versus the actual outcomes, if that makes any sense. So say a very recent, a very apt situation, whether or not someone is positive for COVID-19. I'm sure you've heard the term false positive a lot when it comes to COVID-19 and the quest for a vaccine, right? So as you can kind of deduce, false positive means that the person actually doesn't have COVID-19, but they've been wrongly evaluated to carry COVID-19. So the same goes for this thing. So true positive is like, yes, this person has COVID-19, and the test does show that this person has COVID-19. False positive, I explained earlier, the person is not sick, but the test shows that it's sick. Your false negative is self-explanatory as well. The person actually has COVID-19, but the test somehow mistakes the person as someone who is healthy. And your true negative, yes, it means that the test is correct. So actually, when we evaluate our models, we have three matrices we can turn to. Precision, recall, as well as accuracy. I'll start with accuracy first, because I think that's easier to understand. So accuracy is basically how correct your model is, right? So it's your correct guesses, your correct outcomes, your true positive and your true negative, your truths, over your total. That's pretty okay to understand, right? The tricky part when you look at precision as well as recall, because there's a slight difference between the two, and it's not exactly the same as accuracy as well. So precision is actually answering the question of what proportion of the positive identifications are actually correct. So the formula for precision is actually your true positives, the positives which are actually correct, over all your positives. So it's both the true and the false positives. Whereas recall is answering the question of what proportion of your actual positives is identified correctly. So it takes your true positives, the ones that are actually correct, over all of the positives, like the actual positives. So this one is over all the predicted positives. This one is over all the actual positives. Is anyone lost at this point? Or should I say everyone's confused at this point? I hope not. It's pretty tricky to grasp at first, but give it some time, think about it, sleep on it, and you'll kind of get the nuance and the difference between these three matrices. Yeah. So is everyone okay up to this point? All right. You can also read more about confusion matrices here. I've added the link here you can refer to. So I've already talked about how scikit-learn has so much like libraries, models, etc. They also have like a metrics library for you to test out how well your model stands up. So we're going to import their metrics. This is just some syntax stuff. And from here, we can print out the confusion matrix from our previous prediction. So as you can see, we have 169 false negatives. This one is no? You see that it's predicted to be 0, but it's actually 1. So that's a false positive. This one is a true positive. Wait, did I say? Oh my God, sorry. This is true negative. This is false positive. This is your true positive. And this is your false negative. Yes, sorry. Okay. And using the formula as stated above here, we can check the precision, recall, and accuracy of the model. Or better yet, we can use scikit-learn's inbuilt function for it. Yes, it's just right there. And it will tell you the accuracy, precision, and recall. I mean, you can choose, you can, double check, sanity check, do the maths yourselves, see if it's the same number you get here. Yeah. So our final evaluation of the model is in an ROC curve. So ROC stands for the receiver operating characteristics. and it actually plots your true positive rate against your false positive rate. Yeah. So as you can see, right, there's this funny word called AUC. It stands for the area under the curve, like this area right here. And what it does is it actually indicates like how well your model predicts the outcome. So it's the probability of it predicting the outcome correctly. So obviously the higher your AOC, the better. And we can see that our AOC here is pretty high. 0.8 is actually quite good. So yes, we can safely say that this is a decent model. Is anyone lost up to this point? Does anyone have any questions or anything they'd like to know more about this topic of linear and logistic regression? Everyone's able to run everything, right? Like you're getting some output, you're comprehending what I'm saying. Yeah. I'll give you some more time to explain. If you need like, if you missed out like the input for any of the cells, do let me know as well. Yeah, I'll just slowly scroll through everything one by one. Okay. So let me do a quick recall of our entire exercise. So first, we mounted the Google Colab into our drive so we can access the data right in the workshop folder. We imported our basic libraries. This is pretty standard when you want to do like a exploratory analysis and data science. We imported the data set from the grad admission CSV. And from there, we started our univariate linear regression. First, we created a new data frame from the chance of admission column as well as the CGPA column. We split the data sets accordingly for our linear regression model. Oh, I realized I did not put the test size. Oh, yikes. Okay, that's okay. I'll just arbitrarily put this. So it means that 30% of the data is your test data and 70% is your trained data set. My bad. Okay. So yeah, okay, I'll just rerun everything. Afterwards, we did a correlation of the heat map. You see that it's a strong correlation. I'm going to import linear regression from scikit-learn, fit it into the object, and we have our coefficients and our intercept. We then proceeded to plot the linear regression model against the actual data. We check how well our model is with these matrices. Mean squared error and explain variance. We then predicted your chance of admission based on the test data set. Yeah. And then we evaluated the model for that one as well. Okay, so we move on to multivariate linear regression when we take into consideration other variables. So we extracted the data frame accordingly, split the data set, create the heat map for the correlation of all of the variables, fit the data into our linear regression model. We get the coefficients and the bias, and then predict your chance of admission based on the trained and the test data set respectively. Okay, and that is linear regression. Does anyone have any questions on that? Okay. We also check our model and evaluate it with these matrices. All right. So for logistic regression, we imported the data set, our diabetes data set. We extracted the columns we want to use to determine whether or not someone has diabetes. We split the data set again, imported the logistic regression model, and then fit the data set into set model. Okay. Then we created a heat map. We created the confusion matrix of our final predictions. We calculated the accuracy, precision, and the recall. And finally, we produced our ROC curve. So is there any questions up to this point? Or is there any cell you want me to go back to? Like you didn't manage to fill in the code well, or is everyone okay? Okay. If y'all have no questions already, then that actually concludes the end of our workshop. If y'all still got, you missed out the fill in your code part, I'll just direct you to them. So first you want to import the data set here. So that's one, fill in the code. The next one, I think I put it was here. So your chance of admission, CGPA. Then the next part was for this train test split function. So the sequence is X, Y, and your test size. So that's CGPA, chance, and then 0.3. Okay. Yep. And for this one, if I recall, I put one here. You fit your X train data set, your Y train data set to the linear regression object. Then I think, yeah, I didn't put any fill-ins here. Then for this, you type in this whole chunk. Don't forget the square brackets. I made that mistake earlier. You split your data set, X, followed by Y, and your test size. Yeah. I don't think I put any more fill in the blanks up to this point. Logistic regression is the same thing, your data frame name followed by your CSV file. Split the data set, X, Y, test size. Then, yeah, I think that's about it. So with that, you should have filled in all of the cells. You should be able to like run all the cells, like you can control F9. Yeah. So we've come to the end of our workshop. Thanks so much for joining us, and we hope that you've learned something meaningful. Before that, you do need to fill in a feedback form. Please scan the QR code there and give us feedback so we can improve on future workshops and we'll know what to do better, what not to do next time. Thank you. All right. Anyways, once you're done filling in the form, you can leave the Zoom session. So goodbye and good night.
Hi everyone, so I'm still opening this workshop. So if in case you still have any questions to be asked, you can just private message any of our MLDA team and we will try to respond to you all. And if you already want to go or need to do something else, then you can just leave this workshop because it is already ended. Thank you. Oh, and don't forget to fill in the feedback form because we want to make sure that our next workshops will be better.